Hi, this is Ankita, faculty from Department of Civil Engineering, Christ College of Engineering, Irinjalakuda. And in this lecture, we shall go through the various topics in our Module 5 as per KTU syllabus. The main area is compressibility and consolidation. These are the various topics that we will discuss in order to cover the syllabus portions. And in this lecture, in this particular lecture, we will be going through compressibility and the process of consolidation, its importance, its various stages, and spring analogy model used to explain consolidation, and also the test procedure for consolidation, the various methods, the two methods to determine void ratio at various load increments, and also E log P curve. What is compressibility? If you are applying a compressive load over a soil mass, what happens? Its volume will decrease, and this decrease in volume of that soil mass under stress is known as compression, and the property of that soil mass by which the volume is decreasing under pressure is known as compressibility. So how you can make a soil mass compressed? So what are the possible ways to compress a soil mass? So a soil mass will be having air particles, air and water filled in the voids, and also the soil particles in the case of a partially saturated soil. And if it is fully saturated, there will not be air in the void, it will be fully filled with water. And in a dry soil, there will be only air in the voids. So in such a case, what are the possible ways in all these cases to make the soil compressed? So compression of soils can occur due to one or more of the following causes. What are the causes, or what are the ways by which soil can be compressed? So we can compress the solid particles and water in the voids. So we can either compress the solid particles and water, but usually in a geotechnical engineering practice there will be some loads over that soil, and that loads will not be sufficient enough to compress the solid particles and also compress the water. It may not be enough. So we may take it as solid grains or the soil grains, and the pore water is practically incompressible. So that is not possible. So again, how can we do that compression? So compression of soil, how to achieve it? There is air in the void, so you can either compress and expel the air out of the void. You can make the air move out of the void. So that is a possibility, and that can happen in partially saturated and dry soil where this air is present in the soil mass. And a third way is expulsion of water in the voids, and that is the case, that is the only way for saturated soils. We can expel the water in the voids and make the soil compress. So the expulsion of air and expulsion of water in the soil mass are the primary sources of decreasing the volume, or the primary sources of compressing the soil mass. What is consolidation? It can be defined as the time-dependent process of volume change in soil as water is squeezed from the pores. So if you are considering a saturated soil mass, there will be water in the voids, and the water you are assuming it as incompressible under the normal loads. So the decrease in volume or the compression can happen only if the water is expelled out of the voids. Such a compression can be resulted from a long-term static load. So there should be a long-term static load. It is not changing, it is constant. That static load should be there, and the escape of pore water should be consequent, and that is termed as consolidation, and it is a time dependent phenomenon. So according to Terzaghi, every process involving a decrease in water content of a saturated soil without replacement of water by the air is called consolidation. So you are making the water to go out of the soil mass, but instead air is not coming inside. So that process, okay. So the time dependent process of volume change in soil as water is squeezed from the pores is known as consolidation, and you can relate it to a related to squeezing of water from a saturated sponge. If you are squeezing saturated sponge, water will be coming out, so that also can be related to this consolidation. So when this consolidation is happening, water is escaping, and then the solid particles will be rolling and sliding, and they will be moving from one position to the other to have a closer packing. So there will be decrease in volume of soil due to this rearrangement of soil particles. And some amount of grain fracture or bending may also happen to the soil particles, but it is not much significant when you are considering the ordinary range of load or the stresses involved in soil engineering problems. So there are two distinct or the two main aspects about this volume change behavior. How much is the magnitude of volume change, and also how much is the time required for this volume change under a particular stress. What is the need or importance for studying the consolidation properties of soil? For a civil engineer, how this consolidation of soil is more important? So if you're considering a structure that is having a foundation and the foundation is resting on soil, so the load from the structure is transferred to the soil, and again the soil is getting stressed. So the two most important requirements for stability and safety of the structure are the deformation, that is vertical deformation called settlement of that soil should not be excessive, and that settlement should be within some tolerable or permissible limits. So the building will be settling, or the building will be affected if the soil below that building or below that foundation is going down. If the soil is having some deformation, then the building will be affected. So that is an important requirement for the stability and safety of the structure, that the soil should not have more deformation. The soil settlement or the building settlement of the soil should be within the permissible limits. And also the shear strength of the soil should also be checked. The shear strength, the soil should have enough shear strength to withstand all the stresses induced in that soil. So these two things should be considered for the safety of a structure. And what is the settlement of a structure? It is a vertical downward movement, and it is caused due to the volume decrease of the soil on which it is there. So the structure is over the soil, and if the soil volume is decreasing and the soil is going down, then the building too will go down, and building too will have a vertical downward movement, and it is very gradual, and the gradual sinking of a structure due to compression, that is compression of the soil below, that is called settlement. So again, how this is important, or how this study of consolidation is related to this. Sedimentary deposits and submerged clay strata are invariably found in the fully saturated condition. So there is a chance for expulsion of water from the forceful expulsion of water from the soil mass, and there is a chance for consolidation. So if the structure is made over such a soil, you should study the consolidation properties of that soil. So that is the importance. We can forecast, we can know before the magnitude and time of settlement of a structure made over a particular soil. So that is the importance of studying the consolidation properties. So in this figure you can see a soil mass. It is a fully saturated one, that is the sand particles and water is there. So if a weight is placed over that, if a weight is placed, it is about to be placed over that soil mass before the settlement. It is in a fully in a very good condition, and after placing the weight over the soil mass, what happens? You can see the water is getting expelled out of it. So the volume is decreasing and the building or the soil mass is going down. The volume is decreasing and settlement is happening. And the grains here, it is different. Now it is getting closely packed. And again after the end of settlement, after some more time, what happens? The settlement is more and the water, much of the water have escaped out of the soil, and the grain of sand or the sand grains are having very close packing and it is getting hardened. So this is how settlement is happening. So if you want to know the settlement, if any structure is probable to have a very good settlement after construction, we should be studying about the consolidation properties of that soil over which the building is made. Now, the major types of soil, sand or clay, if you are considering how the difference is coming, how there is difference between the sand and clay. So if you are going to make a building over a particular type of soil, the building is demanding you to have a view of the characteristics of the soil over there. So in a sandy soil, the response under the load will be very instantaneous. The response will be very quick for sand. It is more of a coarse grained type, and if clay, it will take a relatively long time to undergo deformation. And what about the permeability of sand and clay? Permeability will be high. It will allow water to move through it. The permeability will be high for sand, and even during the construction period, drainage will happen. That means the water can drain off from the soil during the construction. During the construction, some weight is laid over the soil, and that weight is enough to drain off the water. But the permeability of clay is very low, and during construction the water is not going out. It is nearly undrained during the construction. Now what about compressibility? For sand, the compressibility is very low, and for clay it is highly compressible. Even up to 1 meter it can go. It can be compressed. And now about consolidation. What is the difference with sand and clay? Consolidation may be generally considered to keep pace with the construction. That means if you are considering sand, if you are talking about a construction over a sandy soil, then the consolidation may happen during the construction stage itself, and the building will not be affected much. The consolidation will be over by the time the construction ends. And what about clay? The consolidation property of clay. Consolidation proceeds long after the construction has been completed. Even after the construction is done, later the consolidation process, it goes on. So that is very dangerous, because once the construction is done and the building is over there or the structure is over there, then if consolidation happens, it will affect the structure, causing settlement of the entire structure. So that is very important in the case of clay. And sand and clay is shown here, and the sedimentary deposits and submerged clay strata are found in nature in the fully saturated condition. So the clay strata will be more subjected to consolidation over a long time. So when saturated clay soil with a low permeability, and if they are subjected to a compressive stress, then the pore water pressure will immediately increase. But because of the low permeability of the soil, there will be a time lag between the application of load and the extrusion of pore water, and the settlement happens. So clay needs greater attention. So if you're talking about consolidation, we'll be much concerned about clay soils than sandy soils. Coming to the various stages of consolidation. Consolidation can happen in 3 different stages: initial, primary and secondary, and out of which primary is of more importance if you're considering the total consolidation. So what is initial consolidation? It is something which happens immediately after the application of load. So consolidation is causing a reduction in volume. So reduction in volume of soil just after the application of load is known as initial consolidation. And in a saturated soil, if you're considering, that initial consolidation will be mainly due to the solid particles getting compressed. And in a partially saturated soil, this will be due to expulsion of air from the voids mainly. And now coming to primary consolidation, that is due to squeezing out of the pore water from a saturated soil that is loaded, and that will be a time dependent process which causes decrease in volume. That is primary consolidation, same as what we have studied or what we have seen in the definition for a consolidation. So after the initial consolidation happens, again the reduction in volume occurs, and that will be due to expulsion of water from the voids. And in fine grained soils, the primary consolidation occurs over a long time. That is, the best example is clay. Primary consolidation will be occurring over a long time if the soil is clay type. And in coarse grained soils, primary consolidation occurs rather quickly due to high permeability, even in gravels. Okay, the third stage is secondary consolidation. This is a reduction in volume that continues at a very slow rate even after initial and primary consolidation is happening. And this is the reduction in volume that continues at a very slow rate even after the primary consolidation is complete. And this is known as secondary consolidation, and this is due to plastic readjustment of solid particles and adsorbed water. And this secondary consolidation is important in the case of peat and soft organic clays. So this happens after the primary consolidation, and it happens only at a very slow rate. Now let's have a look at the spring analogy model proposed by Tasagi to explain the process of primary consolidation. So the entire system is having a cylinder that is fitted with a piston, and there is a valve attached to it, and the cylinder is filled with water, and the piston is having a spring attached to it, and let the stiffness of the spring be 10 millimeters per Newton. And what does that mean? If you are applying 1 Newton, and if the spring is taking that load, it will have a change in length as 10 millimeters. So it will get compressed. If you are giving a compressive load of 1 Newton, the spring will compress by 10 mm. So let the initial length of the spring be 100 mm. Assume that the piston is weightless. So this is the first condition. And now consider that we are applying a 1 Newton load to this piston, and the valve is kept closed. So if you are giving some load over it, somebody have to take that inside. Someone inside has to take that. So the valve is closed, and the entire load is taken by the water inside that cylinder, and the spring is not affected. It is not taking any load. So the load taken by water is 1 Newton, and the load taken by spring is 0. And if you are considering equilibrium of forces, then the load taken by water plus load taken by spring should be equal to the total load. So you can see here, load taken by spring is 0 and the load taken by water is 1 if you are applying 1 Newton with the valve closed. This is initial time t is equal to 0. And now consider the valve being opened. If the valve is gradually opened, what happens? Something is pushing in, so the water will start escaping from the cylinder. And what happens to the spring? The spring will start sharing the load, as more and more water escape from the cylinder, the load carried by the spring will be increasing, and the spring will decrease its length. The spring will get its length decreased, and finally steady conditions will be established and the total load is taken by the spring. So what happens if entire 1 Newton is taken by this spring, which is having a stiffness 10 mm per Newton, its length will be decreased to 90 mm. Length will decrease by 10 mm. Length will decrease by 10 mm, and now its new length will be 90 mm. Now if the load is increased to 2 Newton, again the same thing happens, and the final length of the spring will be 80 mm. Likewise, the process is repeated. So this is how the spring analogy model says. As per Tasagi, this can be now related to the primary consolidation. So we can see how it is related. So how the spring analogy model can be related to the behavior of saturated soil under pressure. So when subjected to steady static pressure, the saturated soils behave in a similar way to that of the spring analogy model. So you can compare the behavior of a spring in the spring analogy model to that of the soil which is subjected to steady static pressure. So the solid particles in saturated soil will behave like the spring, and the water, who will be playing the role of water in the cylinder, it will be the same, water in the voids. Water in the voids will behave like water in the cylinder. And there is a valve in the spring analogy model. So that in the real situation, what will play the role of that valve? The permeability of soil, that is controlling the flow of water away from the soil mass, isn't it? So the permeability of soil controls the flow of water, that is equivalent to the valve in the piston. Then the pore water pressure in the soil. Pore water pressure in the soil will be behaving, or can be compared to the pressure carried by water in the cylinder. And the effective stress developed in soil is the same as the stress developed in the spring. So that's how we can compare the behavior of saturated soil under pressure and also the spring analogy model. So if you are applying a pressure delta sigma, so in the spring analogy model we are applying load like 1 Newton, 2 Newton, and if you are comparing it with the soil mass and a real case, then if you are giving a pressure delta sigma to the soil, to the saturated soil sample of uniform cross-sectional area, the pressure is shared by the solid particles and water, and that can be represented mathematically like delta sigma bar plus U bar is equal to delta sigma. Delta sigma is the total pressure applied to the saturated soil sample. The saturated soil sample is having soil particles and water. So delta sigma, or the sigma bar, is the effective stress, and this is pore water pressure. So you are familiar with this. What is the total stress or the total pressure? It is what is effective stress? It is total stress minus pore water pressure. The same relation is expressed in a different manner. That's all. So initially, just after the application of pressure, the entire load is taken by water. So what will be the equation? There is no load taken by the soil, so this will be 0, and the entire load is taken by water. That will be equal to the total pressure. If you are giving a pressure first pressure, and that is why it is marked as 1. And then as the water escapes, what happens? The applied pressure is transferred from the water to the solids. The solids or the soil particles will start sharing the load, eventually sharing the pressure. Eventually the whole pressure is transferred to the soil solids as the effective stress. So initially this will be the equation, or this will be the condition, and finally what happens? the entire load will be taken by the soil and the load on water will be less, 0. Okay, that is equal to the total load. So as the effective stress increases, the volume of soil decreases, and this decrease in volume is expressed as change in void ratio. So as the effective stress increases, that means if the stress taken by soil increases, the volume of soil decreases, and this decrease in volume we can express it as change in the void ratio. The amount of voids are getting less. Now let's see how this consolidation or how the compressibility of soil can be studied in a laboratory. So this can be done by performing a consolidation test. So the apparatus used for this test is known as consolidometer or odometer, and this apparatus is having a loading frame and a consolidation cell, and the consolidation cell is shown here. And we'll prepare the specimen and place it in the consolidation cell, and we'll keep the consolidation cell over here, and we'll start applying the load, and we'll note down the dial gauge readings, how much is the thickness of the specimen getting reduced. So that's how that's what the test is all about. You will see the detailed procedure in the coming slides. So the result of the test is what? It is a plot between void ratio and effective stress. So I have told earlier that the decrease in volume after consolidation is expressed in terms of void ratio, and the test result will be a plot between void ratio and the effective stress. The void ratio, there are different methods to find the void ratio, and these are the two methods. We will see it later. And height of solids method is general one for both saturated and unsaturated soils, and change in void ratio method is better for it is used for saturated soils. And this consolidation test data or the results are used to determine the following ones: coefficient of volume change, coefficient of consolidation, and coefficient of permeability. So these are some of the uses of consolidation test data. So we'll see how this consolidation test is being performed in lab. So let's see what is the procedure for consolidation test. First, we have to take the consolidation ring, clean it, and take the weight, measure the diameter and height of that consolidation ring to find out the area. And after that, just fill the specimen inside the ring, and take the base plate and keep a porous stone over that. That is a bottom porous stone. And after filling the specimen in the ring, we have to keep a filter paper at the bottom of the ring and place this over that porous stone, and again place a top filter paper and top porous stone over that. And after that, we have to place a loading pad on the top porous stone, and we have to keep this consolidation cell under the loading unit. We have to center it to have the load applied in the axial direction. So we have to center it such that the load applied is axial. So the load should be coming axial over the specimen. So the consolidometer has arrangement for application of the desired load increment, for saturation of sample, and measurement of change in thickness of sample at every stage of consolidation process. So consolidation is something happening in a saturated condition, in a saturated soil. So we have to make the sample saturated. So this consolidometer is having such arrangement, and also we have to give the load increments. So there is an arrangement for that also. And also we have to measure, or we should know how much is the thickness variation of sample under every load increment, how much the sample is getting compressed. So that is that can be known if we measure the height of sample, how much is the variation of height. So that is change in thickness of sample, that also can be measured here. So this consolidometer is having all such arrangements. So once we keep the specimen over the loading unit, then we have to fix the compression dial gauge. We will fix the dial gauge and make the loading arm horizontal, and we have to make it saturated. The sample should be saturated. So that is done by connecting the assembly, mold assembly, to a water reservoir with a plastic tube. So there will be an arrangement to connect a plastic tube that is coming from a water reservoir, and water will be flowing in the consolidometer in the cell, and it will saturate the soil specimen. So the level of water in the reservoir should be approximately same as that of the sample. Okay. So after the specimen is ready for test, we'll start applying the load. So we have to apply an initial pressure of about 0.05 kilogram per centimeter square to the sample, and we'll keep this load till there is no change in the dial gauge reading, or 24 hours, or for 24 hours, whichever is less. And we have to note down that dial gauge reading under this initial pressure of 0.05 kilogram per centimeter square. And after that, we'll give the load in successive increments, like apply the first increment of load, just the double of this, that is 0.1 kilogram per centimeter square. Now we'll apply this pressure, or this load increment, that will give a pressure equal to 0.1 kilogram per centimeter square. And this is applied to the specimen, and we'll take the dial gauge readings at various time intervals is mentioned over here. It may go up to for 24 hours, 1440 minutes. And after that, we'll again double this load increment, that is, instead of 0.1, I will double the load, 0.2 kilogram per centimeter square load intensity. We'll apply such a pressure, and again we will take the dial gauge readings at the various time intervals, and again the same thing is continued. We'll again increase the pressure to 0.4 kilogram per centimeter square, and we'll measure the dial gauge readings at various time intervals. Like that, it goes up to either 6.4 kilogram per centimeter square, or up to the desired load intensity that may happen at site. So up to that value, we'll continue this process. And after completion of consolidation under this particular load intensity, under this desired load intensity as per site conditions, or load intensity that we fix. So after the completion of this, we have to unload the specimen. So this unloading is done in a different way. We have to first reduce the load to 1/4 of the final load. We would have applied some final maximum load now. Now from that stage, we have to unload it. So we have to make that new load 1/4 of that maximum final load. So we'll adjust the load such that it is 1/4 of the final load, and then we'll allow it to stand for 24 hours. So then the sample will take water and it starts swelling, and now we have to note down the dial gauge reading. Again we'll unload, we'll make that load, we'll change that load, we'll apply a new load which is again 1/4 of that load, and we'll make the sample to stand for 24 hours. It will again take water and start swelling, and we'll note the dial gauge reading. And this process goes on until the load intensity is reduced to the very initial value, that is 0.05 kilogram per centimeter square. Again we'll keep it for 24 hours at that load intensity, and we'll have to take the final gauge reading after that time. Then we'll dismantle the assembly. Now the unloading process is done, and we'll dismantle the assembly and take the mass of ring with the specimen, and we have to oven dry the specimen, and with that we can determine the dry mass and final water content of that specimen. We were talking about the procedure of consolidation test, and the result of that can be a plot between the dial gauge reading and time. For a particular typical load increment, if you observe the dial gauge reading and time, if we plot a graph for clay and sand samples, it will be like this: the clay and sand. So initially the decrease in thickness is rapid, but it will later slow down. So if you consider a very small time interval up to this, the change in the thickness, that is change in the dial gauge reading, is very high for sand. And also in the small thickness there is a rapid change in the clay also, but for the clay the entire change is happening over a long period of time. But for sand the major change is happening in a very short time. That is, for sand the change in thickness occurs very quickly. Maybe within a few minutes the result is, or the volume is decreased, because sand is highly permeable and it allows easy flow of water. But for clay it is different. It happens over a long period of time. The result of consolidation test is a plot between void ratio and effective stress. So the decrease in volume or the volume change can be expressed in terms of void ratio, and we can have a plot between void ratio and effective stress. So how to find out this void ratio at various load increments? So we will get the different dial gauge readings at various time intervals. That is what obtained from the consolidation test. So from this height values or the dial gauge reading values, we have to find out the void ratio. So these are the methods to find the void ratio: height of solids method and change in void ratio method. So coming to height of solids method, is very simple. In this method, the equivalent height of solids HS is determined from the dry mass of the soil. So HS is equal to volume of solid divided by area. Height is equal to volume of solid divided by area. So volume can be replaced by, the expression for volume can be replaced by mass by density of the solids. So density of solids is equal to specific gravity of solid into density of water. So that is how it is written here. Then again, what is void ratio? Void ratio is equal to volume of voids divided by volume of solids. That is, volume of voids is total volume minus the solids. That will give you the volume of voids, and divided by volume of solids. So if you write V in terms of area into H, it will be like this. So you will get an expression for void ratio: H minus HS divided by HS. Now the total thickness of sample is measured at the start or end of the test. So we know the total thickness of the sample, and at other stages of loading, H is found from measured thickness and difference in dial gauge readings. So at the start we can measure the total height, and now at various load increments where at different stages, how to find out the total height? It is equal to H0 plus or minus sigma delta H. In change in void ratio method, we can again find the void ratio by the following procedure. We have to assume the specimen is fully saturated by the end of the test. So we know that void ratio E is equal to Wg divided by SR. This basic equation, we know that E is equal to Wg by SR, where SR is equal to 1 for a fully saturated soil. So if you are considering delta H by H is equal to delta V by V, which is equal to delta E divided by 1 plus E. So we can write delta E is equal to 1 plus EF. If you are considering the first and last expression, we can write delta E is equal to 1 plus EF divided by HF into delta H, where E and F will be corresponding values at the final or at the end of the test. So the terms are explained over here as a void ratio and void ratio EF and HF of the sample are known by the end of the test, the void ratio at any other stage can be determined from applying in this equation. EF and HF will be known by the end of the test, so we can find out the void ratio at any other stage by applying this equation by substituting in the change in thickness, and that will be measured by the dial gauge. The change in void ratio under each pressure increment is calculated by working backwards from the known value of void ratio EF at the end of the test after swelling. Please look at these curves. The first graph is variation of void ratio with time when pressure delta sigma 1 is applied. The void ratio is marked over here and time is marked on the x-axis. So this is the graph when the load increment applied is delta sigma 1. So initially the void ratio was this, and when load is applied and if it is sustaining over a time like t is equal to tf, if it is sustaining over a long time period, then the consolidation process is happening and the void ratio is decreasing. That means volume is decreasing, and finally by the end of the test we will have a final void ratio, that is EF1. 1 in the sense it is for a particular load increment of sigma 1, delta sigma 1. So then we can get a similar plot under a pressure delta sigma 2 maybe, and again we can have a similar plot for a pressure delta sigma 3, like that it goes. So every time we will get a final void ratio EF1, EF2, like that. So if you are plotting those values, we will get a curve like this. So this is a curve drawn between final void ratios and corresponding effective stresses for different pressure increments. So for different pressure increments, if we plot the effective stress and final void ratios, we will get a graph like this. So as the effective stress increases, final void ratio decreases. As the effective stress increases, final void ratio decreases and the volume of soil decreases. So remember the spring analogy. As the effective stress increases, that means the soil particles are getting compressed, the volume of soil is going down, the final void ratio is decreasing. So the same variation is visible here. As the effective stress increases, the final void ratio decreases. Delta sigma 5, the value is more because sigma effective stress is varying like this. So this is the maximum value. So the final void ratio corresponding to this maximum effective stress is EF5. That is the minimum value among all the final void ratios. So far we have seen what is consolidation and how it is being explained with the help of spring analogy model, and also what is the procedure for consolidation test. And again we can think of what is a consolidation, what is happening. So if you are loading the soil, it is incompressible and initially the load will be taken. If it is saturated mass, the load will be taken by water, and water is also incompressible, but due to this excess pore water pressure, it will be moving out. Water moves out of this specimen, so slowly the stress is getting shared by the soil. It is getting transferred to the soil, and again due to that the soil particles will be rearranging themselves, and they will be approaching, or they will be trying to be in a stable, closer, compact packing, and that is how this volume change is happening. And so we are much concerned if the curve, E-log P curve. So we are much talking much about this effective stress. So why this effective stress is so much of importance? Because it is the effective stress that is finally transferred to the soil grains, or that is what that is a part of soil grains, and that is causing the volume change that is experienced by the soil. So that is why we are talking more about the effective stress. And consider a curve that is representing the process of loading and loading of a soil specimen, as like we do in a consolidation test. So in the y-axis we are plotting the void ratio, and in the x-axis it is effective stress. So this is a plot between void ratio and effective stress. So initially we are loading the specimen, as in a consolidation test. If you are loading the specimen, this curve represents the loading curve, and after that we will unload the specimen. So this will be representing the unloading part, and again if it is reloaded, the path followed by that will be like this. The variation will be like this, and it goes on continuous with the previous curve. So this is E sigma dash curve, and the variation here, it is not so much linear. It is not linear. So if you are having a much more linear curve, it will be easy for us to have the calculations. We can easily assess the behavior of that particular soil. So that is why it is, again we can see another plot here. It is between E and log sigma dash. That is the effective stress is plotted in a logarithmic scale, and if you observe this portion, that this is this is comparatively a linear variation, or it is comparatively a linear graph. So this will be easy for us to express and to compare the properties or to study the behavior. So there comes the E log P curve. So it is nothing but the expression or the way of expressing the behavior of soil when it is undergoing consolidation. So it is also known as consolidation curve. So we can have E log P curve, or E log sigma dash curve. So now we shall see what are the different parts of this E log P curve. So you can see initial flatter portion. What is it representing? It is marked as recompression. So what is this initial flat portion? What is the significance of that portion? So you're taking a specimen in order to test it under the consolidation test, or in order to perform a consolidation test. We are taking a specimen from a natural deposit, isn't it? So initially that specimen was under some load, maybe the weight of the overlying material or the overburden. So that overburden is removed, and then you are taking that particular specimen and then keeping it for the test. So that overburden is removed, so that soil is having lesser pressure, so it is expanding due to a reduction in the pressure. So if you are starting to load such a specimen, the initial some load will be taken. Initial some load will be having an effect of pre-consolidation. That means it is recompression. So this compression, the soil was in its natural deposit or in its natural state, the soil was already having some compression, but when you took it out of there, it got some that pressure got removed from that soil. So again, if you are loading it in a consolidation test, then some part of the load or some part of the effective stress will be representing the recompression. It is equal to the recompression of the specimen. Then the real consolidation will be starting from A. So what is curve AB? That is the loading curve. Loading curve, it is corresponding to virgin compression. So when the soil was in its natural deposit, or when the soil was in its natural condition, it was already subjected to pressure corresponding to point A. That was its normal pressure. It was experiencing that pressure when it was under when it was a part of the natural deposit. But when you took it, and then again, if you are performing a consolidation test, if you are going with some load increments imposed on that soil specimen, then this is the new loading. So the loading or the increase in effective stress over this part is new to the specimen. This is for the first time the specimen is experiencing that compression. So that is why it is called virgin compression. When a soil is stressed to a level more than what it had experienced ever, then the breakdown of soil structure occurs. So this is the real consolidation now which is happening to the specimen. Then the point A corresponds to pre-consolidation pressure or stress, and the curve AB indicates a decrease in void ratio with an increase in effective stress. It is very clear from the graph itself. And the sample reaches equilibrium at an effective stress corresponding to B. So at an effective stress corresponding to B, the sample is reaching an equilibrium, and then if you are reducing the pressure, if you are unloading it, so this part is representing the unloading, and if you are unloading, we can see here it is unloading, it is corresponding to unloading. If you are unloading it, then the soil is expanding, it is allowed to, if you are unloading it, the soil is the pressure over the soil is reduced and the sample is allowed to swell, it is expanding. So the curve BC is the unloading curve, or it is corresponding to the expansion or swelling. And if it is unloaded, will it go back to the previous stage of void ratio? So initially the void ratio, the amount of voids in the specimen was somewhere here. It was somewhat this amount of void ratio. But if you are again unloading it fully, unloading, the stress is getting reduced, the effective pressure, the pressure is getting reduced, and if you are unloading it fully, it is never going back to its original void ratio. So unloading will not restore soil to original state. So some permanent deformation is occurring, or the permanent deformation has occurred, and that is due to irreversible alteration in the soil structure. So when it is undergoing the consolidation, it will be having some breakdown of the soil structure, it will be experienced, and that due to that it cannot go back to its original previous void ratio. So the void ratio cannot be the same as that before the start of the test. And again, if you are reloading it, again if you reload, that curve is again recompression. What do you mean by recompression? So initially when we had stopped the loading, it is at the point B. So at B it was experiencing some sigma dash. So up to sigma dash now the soil has experienced, and after that we had unloaded that. Again if you are reloading, this range of stress is already experienced by that. So again this part can be considered as a recompression, similar to the previous one. When the soil was in its natural condition, it was having certain, it was under some pressure, so that was up to this. Suppose it is up to this. Okay, so similarly here also we will get a recompression curve. So the pressure or the stress range in this recompression region is already an experienced value. It has reached up to the stress corresponding to B. So that is recompression. And again if you are loading it, that stress the curve is continuing, and it continues as an extension of the curve AB. So after this point, what happens? Now whatever stress is experienced is again new. it is a new stress. It is beyond this value, the stress is increasing. So this part is again a virgin compression type. It is again new to the soil. That much of stress it had never experienced. So this is what E log P curve explains, and this is what E log P curve is all about. And in a consolidation test, we are loading it and unloading it, and if you are reloading it, then we'll get this particular form of the curve. And with this, we come to an end of the first lecture on consolidation. Thank you for watching. Please watch the other lectures also. Thank you.